See, so far we talked about Newton's law, and we have kinematics and Newton's law. In a lot of situations you can calculate stuff if you want and apply Newton's law. But there are some situations that using that is tricky. For example, this situation, if you leave this ball from this position, let's say at angle 60 degrees from vertical, and let it go, or maybe more, let it go, you want to find how fast it's going at this point. How would you do that? If you want to find how fast it's going, you have to know the acceleration. But the acceleration is not constant. If you look, acceleration is depending on this angle. In fact, it will be sine of theta with the horizontal, that theta angle. It's g times sine theta. And then, because it depends on theta, as theta changes, the acceleration changes. One is really, really hard question to answer using kinematics and Newton's law. That is why we have some new stuff about work and energy, which is good for this kind of problem when you cannot apply Newton's law directly. Of course, Newton's law is correct. Nothing wrong with the Newton's law. Everywhere works. But it's sometimes hard to apply if the acceleration is not constant. So we need some other tools, which are exactly the same as Newton's law, but explained another way. So the work and energy we talk about are only some new concepts. Nothing new physically. Everything is still Newton's law. But you can look at them in a different way so that you can address questions like this more easily. So that's what we're going to do. I will bring this down now. Get back to this problem when we develop the tools for this kind of problem. So kinetic energy and work. Kinetic energy denoted by capital K equals to 1/2 mv squared. If something has a mass m and is moving at a speed v, it has this much kinetic energy. That's the definition. What is the unit of kinetic energy? The unit of mass, which is kilogram, times unit of velocity, which is meters per second, squared, right? So meters squared per second squared. We have a name for this. 1 kilogram meter squared per second squared is called 1 joule, and is denoted by capital J, all right? And do you know why kinetic energy is defined like this? That is something that probably you don't know, but I'll show you later on why it is defined like that. For example, if your car is 1500 kilogram and it's going at 90 kilometers an hour, how much kinetic energy does it have? Let's say M 1500 kilogram, that's like an average small car, and V is 90 kilometers per hour, which is 25 meters per second. Calculate how much energy it has. 468,750. Usually say 468 kilojoule. The bigger the object, the more massive the object, the faster it goes, it has more kinetic energy. The next thing we define is work. Work of a force. So if you have a force acting on an object and is moving it a distance d, like a displacement d. Let's say this displacement and this force. And force and displacement have an angle between them, let's call it phi. The work of this force is defined by the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. Does this ring a bell?
Dot product.
Dot product, very good. The work is actually a dot product of force times displacement. All right? If the force is constant over that displacement. Okay? Okay, let's practice. I have this 2 kilogram object. I can move it from here, like up to here, slowly. Right? From here to here. Let's say I move it 80 centimeters from this point to this point. How much work do I do? There's 2 kilogram object going from here to here. And on the way, it's like this 2 kilogram object, and from point A to point B. Yeah.
Would it be 0?
The force that I'm applying is upward, right?
Yeah.
And the displacement is also upward.
Mm-hmm.
So this is the displacement. Let me say, this is the displacement vector, right? And the force that I'm applying is which way?
Up.
Up, right?
Yeah.
This is the that I'm applying. So why is it 0?
Because the angle, right?
The angle between them is 0. But what is cosine of 0?
1.
Cosine of 0 is 1, right?
Yeah.
So will be the force that I'm applying times the displacement. Displacement is at 80 centimeters up, right? So the magnitude of displacement is 0.8 meters. And the force that I'm acting is what? If it is 2 kilograms, take me as 10. How much force? I apply 20 newtons of force. 20 newtons. And then phi is 0. Cosine 0 is 1. 0.8 times 20 is 16, right?
Mm-hmm.
So W is 16. What's the unit?
Joule.
We didn't talk about unit. It's Newton meter. What is Newton? This kilogram meter per second squared is Newton times another meter becomes also joule. This kilogram meters per second squared, that's Newton, right? Times another meter becomes kilogram meter squared per second squared. That's also joules. So it's Newton meter is also equal to joules. So that's 16 joules. The unit of work is also joule. Okay? So they have the same units. Kinetic energy and work. Alright. You see, once I'm moving it from here to here, 80 centimeters up, the gravity, force of gravity is also acting on it, right? So how much is work of gravity? The force of gravity is like this, right? W as mg. That's a magnitude mg, which is 20 Newton again. But what is the work of gravity?
Negative, right?
Why is it negative?
Because it's 180, it's the opposite.
Yes, the angle between D and force is 180 degrees in this case, right? Force of gravity is downward, displacement is upward. So the work will be, work of gravity is magnitude of the force is mg times d times cosine of the angle between them, which is 180 degrees. What is cosine of 180?
-1.
-1. And mg is also 20 Newton, d is the same. So work of gravity is equal to -16 joule. Work of my hand, if I'm moving slowly, it doesn't have acceleration. I have to apply the same force as 20 Newton and go. This is called moving it in equilibrium. Means that it's not accelerating. Very, very slowly you're moving it. It is in equilibrium at any point. All right? What if now I move this object, instead of going from here to here, 80 centimeter, I go like that. Go 80 centimeter up and a meter this way. Like this. At an angle. How much work do I do in this case? So I'm going from point A to point B like that. And if I make horizontal and vertical here, this is still point A. Let's say call it H, is 0.8 meters. And this is, let's say, X. 1 meter. How much work do I do now? And this is the object. And force of gravity applying downward. My force is upward, mg and F, and we're going at equilibrium slowly. So if I want to calculate my work, is how much? The displacement is this way, right? Let's say call it D. D times the force F times cosine of the angle phi. What angle is phi?
Is it the angle between F and D?
Yes, between F and D, this is phi, right? Between the F vector and displacement vector, right? So now I want to calculate this cosine of this. But what is D? Is D the same as 0.8 meters anymore? No. How much is D?
Square root of 1 squared plus 0.8 squared.
Yes, square root of 1 squared plus 0.8 squared. Square root of 1.64, right? So let me keep it as D and F. But what is cosine of phi?
90 minus whatever theta.
You see, if you look at this angle 90 degrees, this is also phi, right? You see there are two parallel lines here, and it's crossing it. So this angle and this angle are the same. What is cosine of phi in this triangle? It's adjacent over hypotenuse, right? Adjacent is h. Hypotenuse is d. Let me write that in here. W will be d times f times h over d. This is magnitude of d, right? And d cancels out. Again, you get f times h. How much was f? In order to hold this, I have to apply 20 Newton, right? Times h, which is 0.8 meter. So the work that I do has to be 16 joules, Newton meter. So you see the work doesn't change. Isn't it odd? Going directly upward or going this way, if you go the same height, the work doesn't change. What if I go from here to here, but I go this way? At first I go from, let's say from A, go to C, and then go to B. If I go from A to C, and then I go from C to B, how much work do I do?
The same amount.
Same.
What is the work of my force if I go from A to C? It's like that. I go first, instead of going this way, I go this way. First I go horizontally to this point and then go up 80 centimeter. What is the work that I'm doing from here to here, going at equilibrium?
Zero.
Why is it 0?
Because there's no D.
No, D is this way.
No, because you said like it's at equilibrium.
Yeah, it is at equilibrium, but I'm going
So it's
through
not
this
moving to
displacement.
equilibrium. Oh.
I'm going through this displacement, right? But the force I'm applying is this way, right?
Oh, cosine of 90 is
Yes.
0.
This is displacement, this is the force. From A to C. Right? The force that I'm applying, because I'm going very slowly at equilibrium. There is no exertion, so again F is vertical, right? They're going very slowly. Force that I'm applying is vertical, I'm going horizontal. The force times displacement times the cosine of the angle here is cosine of 90. What is cosine of 90?
So the situation is if you're moving, not you're moving it.
No, we're moving. You see, I'm moving it very slowly this way. But the force that I'm applying while moving this is up, right? I'm not applying force this way because it doesn't accelerate this way. I'm going slowly, okay? At constant small speed, right?
Okay.
So the force that I'm applying is always vertical. And it's slow. I may take my time to do this in 2 hours, right? So at any point, I'm applying force upward, right? My force is exactly vertical, and displacement is horizontal. The angle between them is 90 degrees. And then if you do d times f times cosine of the angle, cosine of 90 is 0, right? So you get 0 work going from here to here. And how much work from here to here? Again, the same as the problem before, which is f times h, right? Yes.
The force is vertical because of gravity, right? So
The
it's
force of,
counteract-
yeah, because gravity is pushing it downward. In order for me to hold it, I have to push directly upward. And it's no acceleration because it's going at equilibrium, right? So if you're going this way and then go this way, the work will be the same. Now if I go this way first, go to this point P, and then go horizontal this way, how much work do I do this time? The same. See here, I do F times H and then no work here, right? What if I go any other path from here into here? I go like this.
Is it path independent? Like it doesn't matter?
For these 3 paths seem to be the same. Can I say it is the same for all paths? We have to see what we need to do if the path is not straight or the force is not constant. What do we do in that case? So work is like this when the force is constant and the path is straight. Let's say from A to B, you go on a path like this, right? And if you want to do mathematics and put a coordinate system here, this A is in coordinate x of A and y of A. This is a coordinate x of B and y of B. And the x-axis is this way, y-axis is this way. If you want to calculate the whole work, you do split the work into very, very small pieces, going very small distances along the path and calculate a little bit of work for that. Let's say at this point I'm going this distance dl, and then I'm applying a force like that, which is equal to mg upward. To hold it, I have to apply mg, right? I'm going very, very slowly, right? Okay. Then I calculate dw for this small dl. And because this is very, very small, I can make it as small as we want. The work that I do during that small displacement is equal to what? The force, we go back to this. The force that I'm applying times that small displacement. Force that I'm applying dot dl. That's the small work that I'm doing along that dl. But then you add all of the contributions. When we add, what do we call it in calculus? Add small pieces, we call integral. Then w becomes adding all dw's, and that's equal to adding all f dot dl's from A to B. And now if I write this as a vector, the force as a vector that I'm applying has a magnitude mg. In which direction is it? In y direction, right? So can I just say times j hat and make it a vector? is magnitude of the force times j hat, which is in y direction. So that gives you the whole force, right? And then, what is dl? If you go a little bit dl, you get a dx in x direction and dy in the y direction. So dl as a vector is dx I hat plus dy j hat. Right, using the vectors that we worked on before. See, they have dot product. We have these in unit vector notation. How do you do dot product when you have unit vector notation?
You multiply the components.
The components. Yeah. So dw, which is f dot dl, becomes what? Fx, how much is Fx? This is the y component, isn't it? So the x component is 0 times dx, and then mg times dy, right? So it becomes just mg times dy. And then you add these from a to b. So w will be integral from a to b mg dy. What is constant? M is constant, G is constant, because they go out of integral, right? So W is equal to mg integral from a to b dy. Right? What is integral of dy?
Y.
Y. And then put b and a, get y of b and minus y of a. Just how much you go higher. Doesn't matter how much you go horizontally. So W becomes mg times y at b minus y at a. Or in this case, mgh. Right? If this is at height h above this one, that will be mgh. And how much does gravity work while I'm doing this? How much is the work of gravity if I do the same thing for gravitational force? What is the difference for force of gravity? This will be the same, right? But force of gravity is negative mg times j because it is in the negative j direction. So the negative sign comes and becomes negative sign here, right? And becomes work of gravity is equal to mg times yv minus ya, or w, oh sorry, not negative. W becomes negative mg delta y. It's always the case. So this is work of gravity is negative mg delta y. It doesn't depend on the path. It doesn't depend on how much you go in the horizontal direction because the force of gravity is in y direction. And it only depends on how much difference in height you get. If delta y is negative, means that you go downward in y direction. Delta y is negative, it is negative, the work will be positive. If you go upward, work of gravity is negative. Going up, negative, going down, positive. Okay? So that's work of gravity. And you see that it doesn't depend on the path. We did that in three partially straight paths here, but in general, you see that it also works. It's always independent of the path. A force that has this kind of quality, you call it conservative force. So gravity is a conservative force. But in here, only gravitational force is conservative and spring force. And for these, the work done from one point to the other doesn't depend on how you go from one point to the other. And that gives us a tool that we are going to talk about later, but we can define potential energy for these forces. And then we can use that to apply to some situations where Newton's law is hard to apply, as in this situation that I talked about. Okay, so this is important that the work does not depend on the path. The force of a spring in x direction is negative k times x. Right? This x is the distance from the equilibrium, and k shows how strong the spring is. For example, if this is spring in here, and if I apply from equilibrium, let's say this is equilibrium leg, I apply force, it gets some distance from the equilibrium. X is from the equilibrium to this point. And the force that I'm applying is the same as the force that the spring applies. And if x is this way, the force of the spring is that way. That's why you have a negative sign in front of it. Right? If you take a spring, let's say it's at equilibrium here, I go from this point to this point. How much work do I do and how much work the spring does? You want to calculate that. So again, because the force is changing by x, we say W is equal to integral dW. dW is fs x dx, and that will be integral of negative kx dx from, let's say, point x1 to point x2. Right? You go from point x1 to point x2, and W will be negative k comes out, integral from x1 to x2, x dx. And what is the integral of x dx?
X squared over 2.
1/2 x squared. 1/2 can put outside, so it becomes x2 squared minus x1 squared. Right? So W is W of the spring, we call it. So W spring is negative 1/2 k x2 squared minus x1 squared. Usually we take x1 to be at the equilibrium, means x1 is 0, and from equilibrium to any point, x as work of a spring is negative 1/2 kx squared. So if you take x1 to be 0 and x2 to be just x because we don't have x1, then W is spring negative 1/2 k x squared from the equilibrium. This is the work that the spring does from equilibrium to any point x. Okay, so we talked about kinetic energy and we talked about work. Why do we have them in the same topic? How are they related to each other? They are related. Let's say there's an object that can move around a straight line. Let's say from A to B. And this is just a straight line. It is constrained to move along this. And F net acting on it like that, because if it cannot move in the perpendicular direction, some of the forces in that direction is 0, right? So F net only has x component, right? From A to B. And we want to calculate the work of this force from A to B. Let's call W net from A to B. What is that? Because F net is only in that direction, we call that direction x direction. And dl is dx times I hat. F net also is in x direction, so we get integral from A to B, F net magnitude, because it is in the x direction, times dx. Right? But F net is equal to what? MA. So this integral of MA dx, W net, is equal to M integral from A to B of A dx. What is A in terms of other parameters, in terms of x or b? Acceleration was dv over dt, right? You get m integral from a to b and dv over dt and dx, right? And then if I put dv aside and look at dx over dt, what is that?
dv. Or no, that's velocity.
That's v, right? So w from a to b, and we emphasize net force, net work from a to b, is equal to m integral of dx over dt, which is v times dv from a to b. What is integral of v dv?
1/2 v squared.
1/2 v squared. Do you see now why there's 1/2 in the definition of kinetic energy? So it's 1/2 m v squared evaluated at a and b and subtracted. So you have 1/2 mv at b squared minus 1/2 mv at a squared. Right? So W net AB is equal to 1/2 mVb squared minus 1/2 mVa squared, which is kinetic energy at B minus kinetic energy at A. That is why we define kinetic energy as 1/2 mv squared, so that the work done on the object, net work done on the object, will be equal to change of kinetic energy. Otherwise, this wouldn't work. All right? And now, I can drop A and B for any 2 points. Net work is equal to change of kinetic energy. This is our main formula in this chapter. The relationship between work and energy. Net work on any object is equal to change of its kinetic energy. And I want to emphasize that is net, right? Means that some work of the net force or individual works of all the forces acting on the object is equal to change of kinetic energy from any initial to final. This is called work energy theorem. Why is it called a theorem? Because we use F equals ma to derive that. This is equivalent to Newton's law. So it is nothing new, but it is another way of looking at this phenomenon. We're going from one point to another. We can think about the acceleration and how acceleration changes velocity and velocity changes position and so forth, and go from one point to the other. Or we can look at this, how much work is done on it and how much changes kinetic energy, then we can get an equation that has final velocity in it. From there we can find the final velocity. You see, it is the same, but it sometimes is easier to use. So, let's go back to this problem that we had at the beginning. If we start this at, like, let's say, 60-degree angle, or any other angle, 90 degree, right? And let it go. It gets to this bottom point and has some speed. Let's say we want to find how fast it's moving at that point. All right? As I said, because the acceleration is changing, it changes in here, acceleration is g. And here, acceleration is almost 0. It changes from g to 0 with position. And if you want to apply Newton's law, it will be an extremely hard problem. It's actually not analytically solved. If you want to solve this, you have to use series and integrate term by term and make infinite series and do all of that. It will be very hard. But let's say now start from 60 degrees, let's say from vertical, and then go to the bottom. How fast is it moving when it's going to the bottom? So let's apply these principles. By the way, this was for 1 dimension. It is correct also in 2 or 3 dimensions. Let me show you how it works in 2 or 3 dimensions. If the path is in 2 dimension, you can extend it easily to 3 dimension. Like in here, we have the path in 2 dimension, right? It's not going on a straight line. It's going in 2 directions. Let's say the path is going like this from A to B. And we put that in a coordinate system again, x and y. We take, at any point, there are forces acting on it. The F net is this way now, and the dl is this way along the path. We take dl again. F net has 2 components. Let me drop the net. We know it's F net, but drop the net so I don't have to write it all the time. Fx I hat plus Fy j hat. Right? And then if you have 3 dimension, you have the third one, Fz k hat. But it is the same. And dl again is dx I hat plus dy j hat. If you like mathematics, this should be really interesting to you, how the math works. The way I like to teach is to highlight the application of math in physics, how we use it actually. All of these things that we talk about in math is very, very useful in physics. The most intensive use of math is in physics. So if I want to calculate total work from A to B, W from A to B is equal to, of course, W net means work of the net force. The integral from A to B on this path, and this path, this particular path or any other path, will be F net dot dl, right? So adding all these small pieces together to get the total work, right? And what is F net dot dl? Will be Fx dx plus Fy dy, right? So we get W equal to integral from A to B Fx dx, means x component times dx, plus integral from A to B Fy dy. And the same as what we did just now, can write this as acceleration in x direction. Acceleration in x direction, let me do one of them. And from A to B, you get m ax dx, and m comes out, comes dvx over dt dx. And then dx over dt becomes vx, right? From A to B becomes m integral vx dvx from A to B becomes 1/2 vx squared, right? But put b and a, so it becomes 1/2 m vbx squared plus vax squared, right? As you put a and b, you're talking about only the x components, minus. Putting upper limit minus lower limit, right? That's how we do integral. And this is for the first one. If you do for the second one, it says you have plus 1/2 m vby squared minus vy squared, right? You have all y's, b minus a, right? And now if you add them together, what do you get? If you add, so the total W net from A to B will be 1/2 m, 1/2 m. You put this term with this term, vbx squared, vby squared, added together, right? vbx squared plus vby squared minus these two together, VA x squared plus VA y squared. What is this? X component, y component of VB squared added becomes
the square of the magnitude.
the square of the magnitude at point B, right? So it becomes 1/2 m VB squared. That one becomes what? It becomes 1/2 mv squared minus 1/2 m. This will be VA squared. Right? So this is general W net is final kinetic energy minus initial kinetic energy. Right? It is true for all cases. 3-dimensional, 2-dimensional, 1-dimensional, it doesn't matter. So this is, even though we talked about it in 1 dimension, it is correct in any direction, any 2 or 3 dimensions. All right, now let's apply it to this one. Now we have, this is the pendulum from vertical position. We start from a 60-degree angle here and has a mass m and has a length L. We can measure the length, right? Let's say 75 centimeter or something. And then this swings on a circle, right? Like that, it comes to this point, right? It comes to this point, and this is also L, because this is on a circle, right? The length doesn't change. All right. We take this initial situation, let's say point A, this is point B. We apply this, we say W net is equal to K at point B minus K at point A. If we leave this from here at rest, then K at A is what? If the speed is 0, if it's starting from rest, then Ka is 0, right? So this goes away. So the net work acting on this ball is equal to final kinetic energy here, right? And final kinetic energy is 1/2 mv squared, means V at this point squared, right? And now we need to find the net work acting on it. So the net W net is only equal to 1/2 m VB squared. Now the question is, how much work is done on this? How many forces are acting on it?
Gravity, for sure.
Force of gravity, just this way, and it's mg.
Tension.
Tension force, which is in the radial direction, T. As this is going this way, let's say for every dl that we go in this direction, what is the work of tension force? Well, tension is always in the radial direction, but motion is in perpendicular direction to that. Remember the radial direction and tangent to the, yes, it will be T dot ds or dl at all points is 0. So if the force stays perpendicular to the direction of motion, there's no work being done by that. So W net will be W of gravity plus W of the tension force, right? But this one is 0, we know, because it's always perpendicular to dl. Equal to 1/2 m VB squared. What is work of gravity? We just said it is independent of the path, right? And only depends on how far you go in the vertical direction. So work of gravity negative mg times delta y. is YB minus YA equal to 1/2 MVB squared. M cancels out. And delta Y is the Y of B minus Y of A. So if I make horizontal here, X and Y, what is YA and what is YB? Y at point A is L minus L cosine 60, right? And then Y at point B is 0, right? If you put x-axis there. So how much is that one? It becomes L times 1 minus cosine 60. Cosine 60 is 1/2. 1 minus 1/2 is 1/2 is 1/2 L. So YB minus YA is negative, is 0 minus 1/2 L. Right? So negative 1/2 L. And we put that in here, it cancels this negative sign. Okay? So it becomes negative G times negative 1/2 L equal to 1/2 VB squared. Negative cancels, 1/2 cancel, VB will be GL. We have square root of GL. So VB squared becomes G times L. And you can calculate that. If you measure L from 60 degrees, it has that much speed when it gets to the bottom, right? This problem is extremely hard if you apply Newton's law. But this work energy theorem gives you a tool to find the answer in this case, where Newton's law is hard to apply. So that's the benefit of this kind of approach. And next time, we're going to introduce a potential function for the conservative forces. We have potential, and then we use potential energy instead of work. And then there will be conservation of energy. We use conservation of energy. So that's another way of looking at it again. Instead of saying the work is being done, we say no, it has potential energy changes, therefore kinetic energy changes because they are related to each other. We have conservation of energy. This is the way things go. So there's nothing new, but it's another way of looking at the same physical phenomenon. Okay.